There are two types of vector products, a dot product and a cross product. And so both of these are pretty important, but the cross product especially, and I'll explain why and what these are. But first off, the dot product, you don't use it too much. It's supposed to be like a representation of how much one vector is going in the direction of another vector. I think it's derived from like the vector projection formula or something, which again is just another way of like how much a vector is going in the direction of another vector. It's just, yeah, it's stuff related to that. But really the biggest thing we use dot product for is determining whether a vector is perpendicular or orthogonal to another vector. So if we have two vectors, they are perpendicular if their their dot product is 0. Like, let's take, for example, these two vectors, 4, 3, and 9, and -1. The dot product of any two vectors, so u times v, and the dot product is shown like this. That's how you differentiate between a cross product and a dot product. This is a cross product, and the dot product is, a dot. You do this by basically multiplying the components together. So like you multiply the x components together, and then you add it to the product of the y components, and you do that for however many components you have. So this, for example, would be this would be u of x, v of x, plus u of y, v of y. And in this case, this is 4 times 9 plus 3 times -1. And this is 36 minus 3, or 33, which is not 0. And I'm sure you did not even need this formula to know, that these vectors were not perpendicular. But, for example, take these vectors. The dot product of this is 5 times 6, right? Those are the x components, plus 3 times the -10. And this is equal to 30 minus 30, which is 0. So these two vectors are perpendicular to each other, as you might have been able to guess just by looking at this. But that's technically how we'd figure it out using the dot product. Okay, next up we have the cross product. Okay, the cross product is, in my opinion, it's a very, very cool thing. The cross product shows you actually the normal vector, two vectors, and what a normal vector is just a fancy word for a perpendicular vector. But this works for like if you have a two-dimensional vector, it'll help you find the perpendicular vector to that. If you have two three-dimensional vectors, so they look like this, like you have, let's just draw this in a three-dimensional plane. I know these will look pretty two-dimensional, but like let's say these are your two-dimensional vectors. Your three-dimensional vectors. And you need to find the third vector that's perpendicular, because these two are. The cross product will help you find this vector that is at a right angle to both that vector and that vector, which I think is pretty cool, and that applies for, all dimensions. Okay, so the way we do this is, let's start with a simple example, just so you can see that this works. So let's try to find the perpendicular vector, the normal vector, to 2, 1. This is simple enough. So there's a lot of ways to get the cross product. My favorite way is by putting it into a matrix, and then all you need to do is just take the determinant. So we always, in the top row, we put the coefficients. Since it's a two-dimensional matrix, you're just going to have I and j, and then you put 2, 1. You take the determinant of this matrix, and you get this. So 1i. Actually, the circle makes it kind of hard, but the determinant of this is just going to be 1i, so just I, minus 2j. And this is just the vector 1, -2. Are these vectors perpendicular? Let's see. We're going to take the dot product to see if they're perpendicular. So, actually, let's use the actual word, which is normal. Are these vectors normal? If you've heard of like normal force, it's kind of the same idea. So the dot product is 2 times 1 plus 1 times negative 2. Wow, this is 2 minus 2, which is 0. So these vectors are normal. Okay, now let's try this with a 3 by 3 vector. So we need to find the perpendicular, the normal vector to two 3-dimensional vectors, right, which I drew out for you before. So in this case, it's very, very similar. We have I, J, K this time because, 3 dimensions. And let's see some simple numbers like negative 2, 0, 3, 5, 1, 2. Okay, these are going to be our vectors. Negative 2, 0, 3, and 5, 1, 2. Those are our vectors. We need to find the normal vector. We just take the determinant of this. And so remember, for this one, what we want to do is we want to cover up the rows we're not using. So let's go across the row. I typically go down the column when I take a determinant, but since our coefficients are up at the top, I'm just going to go across. So we're going to start at I. We're going to ignore this and take the determinant of this submatrix, right, and use the coefficient I. So we get 0 times 2, which is just 0, but I'll write it out, minus 1 times 3, and then that's the coefficient of I. And then remember, when we do the second one, our signs alternate, so like J is going to be negative, and so we're going to subtract whatever this is, and this time we cover up those two rows, and we get negative 2 times 2 minus 3 times 5, J, and I'm just going to go down here, plus, and now we have K, this is positive. We cover up those two rows, and we get negative 2 times 1 minus 0 times 5, K. And now we just solve this out. So this becomes negative 3I plus negative 4 minus 15. So minus negative 19J, which is plus 19J. And then plus negative 2K, so minus 2K. Now, the moment of truth. Let's see if these vectors are actually truly perpendicular. So first, let's test this vector, which we'll call vector 1. Is this vector normal to vector 1? So we have negative 3 times negative 2 plus 19 times 0 plus negative 2 times 3. 6 minus 6 equals 0. Check. It is normal to that vector. Okay, now let's try this vector, vector 2. Is it normal to vector 2? Well, we have negative 3 times 5 plus 19 times 1 minus 2 times 2. And wow, would you look at that? We have 15 plus 19 minus 4, which equals 0. So it's normal to vector 2 as well. And now we have three-dimensional vectors that are all normal to each other. So now that you know dot product and cross product, the basics, there are some rules that do pop up a bit. I don't want to go into these in depth, but I think they're a little interesting. I do tend to see these more than I see these. So I would at least try to remember these. Like E is pretty simple, right? Like, come on, you can memorize E. I think it is worth noting that vectors, just like matrices, are not commutative. You can't change the order of things just because you feel like it. No, if it's U and then the cross product U, and then cross product with V, you can't just do V cross product U. It has to be the negative of that. And I suspect that does have something to do with like alternating signs, because when you switch columns in a matrix, you do have to switch signs for the determinant. Something like that, I'm sure. And I'm sure if you wanted to know the specifics, you could look up some proofs, watch some other videos. This one is pretty interesting. It does seem that you can distribute when it's a cross product. This is a scalar. K is a scalar in this. So it's telling you that when you take the cross product of two things and then you multiply it by a scalar, you can just scale up a vector and then take the cross product of something else, which, is interesting. But I would just, again, take a closer look at these if you need to. But yeah, this is cool. I would recommend going into it on your own.